Okay, here I am in my kitchen because of COVID-19. I thought I'd do a demonstration of measuring viscosity with a spindle viscometer. You'll get to use this instrument in lab number 1, and it's also relevant for our discussion of dynamic viscosity in chapter 1. So what I've got here is a container full of water and green dishwashing liquid. I've added some dishwashing liquid to make the fluid more viscous, and we're going to measure its viscosity. I should mention that this type of commercial viscometer is widely used in any industry where you manufacture fluids or liquids. So in the food industry, it'd be used for quality control of products like soups and things like that. It's used in the pharmaceutical industry, in the chemical industry, and in industries where viscosity is really critical, like in paints. You'd use it to control the quality of the product. So what we have here is I've attached here a spindle on this viscometer. This is spindle number 61 that I've attached. Let me just make sure it's nice and firmly attached. Yes. And the way this instrument works is this spindle rotates in the fluid, and the instrument measures the torque required to overcome the viscous shear stress at the surface of the spindle. And for a given spindle, there's a calibration curve that relates the torque to the dynamic viscosity. Okay, so let's go ahead and lower this into the fluid. There's a little handle here. We can lower the spindle into the fluid. And there's a little, probably can't see it, but there's a little notch on the shaft that tells you where it has to be in the proper location. And then we center it. Okay, and we're ready to go. Let me just recompose the shot. Okay, the spindle's been lowered into the fluid and we're in position here. Let me show the controls here. So you've got control over the speed. This is the speed in RPM. I'm going to set it to 30 RPM. I mentioned the spindle number was 61, so you have to have that spindle number selected in the spindle catalog. And now we're ready to turn on the motor and let the spindle rotate. It flashes and it continues to flash until the measurement comes to steady state. And so we can see we have a viscosity of about 47.6 centipois. And what this percentage number here is the percentage of the maximum torque that the instrument can measure. So right now we're using about 23.7% of that torque. And if you press the range button here, you can see that 100% torque corresponds to 200 centipois. And according to the calibration of the instrument, the viscosity is accurate to plus or minus 1% of the full range of torque. So this measurement, 47 centipois, is plus or minus 2 centipois. Okay, so we can go ahead and, so we got something around 47 centipois. We can go ahead and increase the RPM. So since we have lots of torque left over, so we will go up to 60 RPM, and we should see the torque double. So we were somewhere around 46%, which is true, and we should get more or less the same value for viscosity. Now, of course, we're shearing the fluid at a faster rate. We're shearing it at 60 RPM instead of 30 RPM. And we get the same viscosity because this fluid is Newtonian. The viscosity is independent of the rate of shear. So the fact that we get the same viscosity within the accuracy of the range, and by the way, the accuracy of this range is, of course, the full scale is 100 centipois at full torque. So that'll be about 45 centipois plus or minus 1. And we've still got some torque available, so we can increase this to 100 RPM and make another measurement. We'll let it stabilize. So again, we're getting around 45 centipois, and the accuracy, the full scale torque would be 60 centipois, so this is plus or minus 0.6 centipois. So the viscosity of this dishwashing liquid and water mixture is about 45 centipois. I should point out that the viscosity of pure water at room temperature is about 1 centipois. So this mixture is about 45 times the viscosity of pure water. So that completes the measurement of viscosity for a Newtonian fluid. Okay, in the previous video, we measured the viscosity of this mixture of dish soap and water, and we found that when we changed the spindle speed on the rotational viscometer, we got the same, or more or less the same, viscosity independent of the rate at which you were shearing the fluid. That is a Newtonian fluid. That's the behavior of a Newtonian fluid. So for fun, since we've got this new instrument and I've been having some fun with it, I thought I'd try measuring the viscosity of a highly non-Newtonian fluid. And the easiest one to make is a mixture of cornstarch and water. And I would suggest, if you've never done this, go and buy yourself for a couple of bucks a box of cornstarch from the grocery store and mix it with water. You will find that it is quite an amazingly strange fluid. Let me just show you what I mean. If you stir it gently, it looks like a regular fluid, but if you try to shear it quickly, its viscosity increases very rapidly. It's what's called shear thickening or dilatant. And so you can get a sense here of how very unusual this fluid is. Okay, so let's have a go. Let's see what the viscosity of this fluid is, or how it varies with the shear rate. Now I've changed the spindle here. The spindle in this case last time was number 61. It was a much bigger spindle. I've changed it to a much smaller spindle because I'm expecting very high viscosities when I have high rotational rates of the spindle. So let's insert this, and okay, up to the notch. There we go. I might just reframe this image so you can see it a bit better. Zoom in. Okay, so as I mentioned, I have the spindle selected, number 62, the slightly smaller spindle. I'm going to set off at a rotational rate of 30 RPM. Okay, I think we're ready. We can start the motor going and see what kind of viscosity we get. Okay, so we're getting a viscosity about 152 centipois, using only 15% of the available torque on the instrument. Somewhere in the neighborhood of 150, 160, somewhere around there. So in the previous measurement with the water and soap, which was Newtonian, we increased the shaft speed, the rotational speed, and we got the same value for viscosity. But this is shear thickening. So as we go from 30 RPM to 60 RPM, we're going to be shearing this fluid at a much higher rate. And you can see, sure enough, the viscosity goes up. Not that much in this case, 200 and, 18, 19, 20 in that neighborhood. You can see it's kind of oscillating around quite a bit. And let's see what happens if we go up even higher. It's 100 RPM. Oh, and you can see the machine has gone momentarily. That triple or the quadruple E means it's gone off scale. So what's happening here is the spindle turns at 100 RPM. It maximizes out the torque. The motor stops. That reduces the speed of the spindle, which reduces the viscosity, and you can see it oscillating on and off. So you can see you get much different behavior. You don't get the same viscosity. In fact, what's happening is the viscosity is going off the maximum for the range. It's going above 300. Let's go back down to 60 and you can get some idea. So the lesson here is that for a non-Newtonian fluid like this one, this is shear thickening, the viscosity is strongly dependent upon the shear rate. Whereas for Newtonian fluids, which is almost every fluid you'll deal with in most of your engineering practice, the viscosity does not depend upon shear rate. That's the definition of a Newtonian fluid. And that completes this video.